Hello and welcome to Team 24's presentation for Project 2, the Smog-Free Tower. Team 24 consists of Jonathan Papp, Avery Bennett, Aidan Finnegan, and Ashwin Ganesh. As air became more polluted, residents developed an increasing number of lung diseases, and economic activity slowed. It became clear to the Hong Kong government that work needed to be done to clean their air. Therefore, in 1986, it established the Environmental Protection Department, or the EPD, and they revamped it in 2005. The EPD's effort have created a noticeable improvement for the air quality of Hong Kong, but there's still a lot of work left to be done. For example, from 2013 to 2018, ambient concentrations of all major air pollutants dropped from 54% to 26%, and on the roadside they dropped from 68 to 36%. This decrease in particulate matter has improved air quality and the quality of life to a certain extent. However, these numbers are still too high. The Hong Kong government is now striving to reach the World Health Organization's air quality objective guidelines, which are as follows. PM 2.5, which is particulate matter of diameter 2.5 micrometers or less, of an annual mean of 10 micrograms per cubic meter. PM 10, of an annual mean of 20 micrograms per cubic meter. Ozone, at an 8-hour mean of 100 micrograms per cubic meter. Nitrogen dioxide at an annual mean of 40 micrograms per cubic meter, and sulfur dioxide at a 24-hour mean of 20 micrograms per cubic meter. The World Health Organization has set these guidelines as goals based off of levels safe for human consumption. Hong Kong's EPD has identified 4 main contributors to today's air quality problems. The first is emissions from road traffic. The second is similar but different, emissions from marine traffic, as Hong Kong is a significant maritime port. Next, emissions from local power plants, specifically those that are coal burning. Finally, the regional air quality from other countries. Dutch artist Dan Rosegaard has created a 7-meter smog-free tower that he claims attracts smog particles from the air, cleans them, and expels clean air with up to 70% efficiency. However, critics of his work claim that it is not nearly as effective as he claims. It would be very expensive and non-practical to implement, and that it may even contribute to the pollution by adding ozone to the air. If Rosegaard's work is not feasible, the Hong Kong government must find a new way to solve their air pollution problem. So they've hired us.
The primary technology inside of the smog-free tower is the Electrostatic Precipitator, or ESP. The ESP works by taking in air from the outside and separating the particulate out using the corona effect. This particulate is deposited onto collector plates, where it is then put into waste areas. The ESP is generally very effective at its job, but there are a couple of things to keep in mind while using it. Firstly, it's important that voltage is applied to the plate such that the majority of charged particles are moved in the correct direction. This is important for making sure the corona effect works properly. The typical ESP has a few minor sensitivity issues. These include fluctuations in the gas stream causing inconsistencies in the process, and some air can bypass the charging zones. This air is known as sneakage. Other than this, there are a couple of ways in which the ESP may inadvertently release particles back into the air. Typically, an ESP will use some kind of wrapping system to dislodge the particulate from the collector plates. In this process, a portion of the particulate may be released back into the airstream. Studies have shown that coal fly ash, for example, can release up to 12% of its mass back into the air. On top of this, there are a couple more major technical issues with the traditional ESP design. Firstly, the typical ESP uses wire discharge electrodes, which essentially consist of long wires that hang between the collector plates. These electrodes require frequent maintenance due to their relative size and fragility. External environmental factors can cause corrosion at the top of the wires. Additionally, their length can cause them to touch the plates, potentially causing wear and tear. The easiest solution to this is to use dry, rigid discharge electrodes, which should eliminate most of the maintenance problems that come with the wire discharge electrodes. Another problem that can occur with the typical ESP design has to do with the charge of the particles. About 30% of the haze particles that enter the ESP will be negatively charged. Due to the way that the corona effect works, these negatively charged particles have a chance of entering the corona and contaminating it, causing it to work less efficiently over time. The easiest solution to this involves a small adjustment to the internal design of the ESP. Using a series of positively and negatively charged plates will separate out both the positively and negatively charged particles. The remaining neutral particles will be processed by the corona effect, resulting in an output of completely clean air. All in all, despite some minor sensitivity issues, the ESP has been shown to be a fairly effective way of cleaning smog and other particulate out of air.
Okay, so according to both professional analysis done on Rosegard's work as well as our own conclusions based on our own analysis, we've concluded that the PM 2.5 particle specifically, that the concentration of that particle does go down over time as an electric field is applied to the air. So it is clear that for a single case study, the device can achieve the accomplished purification with some catches. Firstly, the height of the purified airspace is completely dependent on the voltage applied to the electrode plate on the device itself. This is one potential problem with upscaling the technology to an entire citywide area, as with many hundreds or thousands of the machines, a huge investment in electricity to actually purify the airspace above the devices would be needed. There is really little to do about this electricity consumption, as it is vital towards charging the air particles to dry in the haze. So there's not much that can be done about this problem. However, additionally, according to the analysis performed on the system, efficiently utilizing this electricity to remove as much haze as possible requires foreknowledge of the ratio of positive to negatively charged particles. So for one system, this is fine, as you can calculate that. However, were the city to upscale to many hundreds of machines, advanced knowledge of all airspaces at any given time would need to be known. This is overcomable, though, as an initial setting could be applied to all the precipitators, and then the efficiency data from this initial run-through could be used to compensate in a second wave of voltage. But this means, though, that the electrostatic precipitator, when optimized, is most efficient at controlling anthropogenic emissions, such as coal combustion, or in places where the city or the research team already knows the composition of the air. So it is our belief that rather than upscale the system citywide, where it could be unreliable and thus counterproductive in some cases, that it is upscaled to very specific locations, such as coal combustion chimneys or exhaust, some of that stuff, to maximize their effective use on cutting down on the harmful particles.
As previously stated, these towers would likely be costly to build and maintain, probably costing in the millions to build, and we would need many of them to cover an entire city. Furthermore, as far as environmental sustainability goes, critics claim that these smog-free towers expel ozone as they clean the air. Inhalation of ozone causes chest pain, coughing, throat irritation, and lung disease in humans, effectively reversing the cleaning the air that it does and contributing to the smog problem.
The use of smog-free towers is a good step, but adding a couple smog-free towers around a city will not make a difference in the amount of smog. In general, the goal should be to stop the smog from occurring in the first place. We need to stop it from the source. The main source of smog in Hong Kong comes from diesel and vessels, marine vessels, and power plants. If we can limit the particles coming from those sources, it would be much more efficient than having a few smog-free towers around town. While technology has come a long way in green technology in these areas, it still has a long way to go, especially for power plants. In Hong Kong, major air pollutants have dropped from 28% to 54%, as stated by a research article from the Hong Kong government. This drop is due to stopping pollutants at their source, with new technology and restrictions on cars and other emitters. Once these particles get into the air, they can travel wherever they want, and it is inefficient to try and capture them out of the air once they disperse. These towers need to be put and implemented where the smog density is the highest to be most effective. Where else is the smog density higher than its source? The team's proposal is that the smog-free towers work with car, marine vessel, and power plant companies to implement this technology into their products. It would be easy to implement this technology in cars and other emitters. This would also make it easier to catch these particles out of our air. According to our model, which we modeled in Python, it is hard and inefficient to catch particles out of the air, and the smog-free tower does not do a very good job of pulling the particles out of the air. So if you implement this on an exhaust pipe, you already know where the emissions are coming from instead of blindly catching them out of the air. The overall goal should be electric power, but until then, putting this technology on the above emitters could be the best way to implement this beneficial technology. One long-term probability with these towers is that eventually they will become useless. Once technology catches up to our time and electric power becomes mainstream, there will be very little smog in the air, hopefully. At least, once this happens, the smog towers will look nice as sculptures in a park. But if you implement a ton of these around the city, eventually you will have to get rid of them somehow. Disposing of a technology like this can be harmful to the environment if done incorrectly. A robust disposal method would have to be implemented by the city if these towers became unused. Also, their lifespan could cause another issue. These are very intricate designs, and they have many parts that can stop working, such as the corona, as mentioned before. If many of these are built around the city, chances of some of them do not work as planned. There is no easy way to tell if these towers are working either. The city would need maintenance people to check to make sure they are working, and figure out a way to fix them if they are not. Overall, they might cause a bigger hassle than they are worth. Overall, the smog-free towers do work a little bit as they are said, but they can be implemented in better ways.